And now it's my pleasure and privilege to introduce Dr. David Jacques. He's a professor of systems engineering within the Department of Systems Engineering and Management at Air Force Institute of Technology, or AFIT. Dr. Jacques joined AFIT faculty as a military member in 1999 and became a civilian faculty member in 2004 upon retirement from active duty in the Air Force. In prior military assignments, he served in various capacities associated with development planning, research and development tests, and intelligent analysis of foreign weapon systems. Within the SERC, Dr. Jacques leads the AFIT efforts with the longstanding Systems, Qualities, Ontology, Trade Space, and Affordability Research Project, or the LT's Trade Space and Affordability Project, which is a now 7-year effort uniting 9 of the SERC collaborating universities. Dr. Jacques' research interests include effectiveness of wide area search systems, cooperative behavior, and control of unmanned air vehicles and munitions, and early application of systems engineering for concept definition and requirements definition. With that, I'll turn it over to you.
Good afternoon, and thank you all for joining us for this talk. Let me go ahead and switch gears to my slides. First, right up front, I want to acknowledge my colleague here, Jeremy Gray, who is sitting in on this on my end. He's been instrumental in doing this work with me. He's also a former student of mine, going back a couple of years, but he's been working as a staff engineer in the Autonomy and Navigation Technology Center now for, what, 4 years now? For about 4 years. So this is some work that we've both been putting together to try and bring together some otherwise disparate set of research projects. And so that's what we're going to talk about today. The problem statement of maybe a little bit of what problem we're trying to solve here. We've got multiple projects spanning multiple faculty members. Many of them span multiple student cycles, and student cycles are, most of our master's students are here for 18 months. We get about 12, maybe 12 months worth of research with them, with the first 6 months being really coursework. With that, we too often have a lack of continuity across projects. We always want to accelerate some of the domain learning so that we can get students into the useful research aspects much sooner in their program. Especially with the experimental work that we do, all of these projects are multidisciplinary. Myself in particular, I tend to recruit students from across the academic programs and the academic departments, and so we always need help trying to bring the students up to speed on the domains that they're less comfortable with. The other thing is, although I'm an SE faculty member, a lot of the students I work with are not SE students, and so I'm always looking for ways to teach them SE without requiring them to go through a full program. And so the use of the reference architectures that I want to talk about is really to help accelerate that learning, but also to accelerate the pace of the research itself. So reference architectures, for those of you that may be a little bit unfamiliar, let me give you some definitions and some examples of this. The definition I'm providing here is, and then the roles here, these are really provided by another paper, Rob Cloutier and some of his co-authors talked about some of the roles of reference architectures: common language, consistency of implementation, supporting validation, and encouraging adherence to common standards. So those are all things that we're trying to take advantage of in the reference architectures that we're developing here. A couple of examples real quick. Mason, and if I butcher some of these names, I apologize, especially if some of these individuals happen to be online here. please accept my apologies if I butcher your name. But Mason and Volsard did one for early warning systems. Provided an understanding of functional elements, served as a basis for design and implementation, and again, encouraging reuse of modules. Cruzy and Wolfert did one for farm software ecosystems, intelligent.
Okay, so getting back to the reference architecture example. So Branscombe Paredes looked at one supporting vehicle architecture. Their reference architecture was really only one component of it. But again, providing a common understanding of functional elements. And then another one, Bayer and Torngren, looked at another one for, this was it for autonomous trucks. And guidelines for instantiation into a prototype system were provided. And again, their application was for adaptive cruise control for heavy duty trucks, convoying trucks and things like that. And then finally, why they didn't call it a reference architecture, there's another group led by Caslow, Ayers, there was some other folks that were working with them on a CubeSat. They called it a CubeSat reference model. They're working with OMG and Incosi on this to help make it a standard. And their desire is to help CubeSat developers proceed more rapidly from conceptual need to on-orbit operations. Provides logical, reusable architecture. Probably the big thing that we're doing that they weren't is we are going a little bit further in terms of providing a component library useful for typical builds. They stayed away from the more detailed hardware definition in their reference model. Okay, a little bit of background on why we're doing this, the type of things going on. In the education area, we actually do a 3-course graduate sequence for a small UAS. It covers conceptualization through design, build, and flight tests using a sponsored project. We emphasize a disciplined but rapid prototyping approach. 9 months for the classwork, and for those students that may want to go on and do flight tests as part of their research efforts, it's kind of an instrumental stepping stone towards getting there. Some of the research efforts that we've done in the past couple of years are listed here. We did auto routing, convoy following, a couple of different iterations of close formation keeping or swarm behavior. We've got other faculty working in the human control area, and then even outside the UAS area, some space proximity operations and other autonomous space maneuvers. Other things going on here. So with this, okay, there's actually been 2 reference architectures that we're developing. One is, we're going to call it the Autonomous System Reference Architecture. It's really more focused on the research aspects, in particular research for new autonomy concepts. It's intended to be domain agnostic, and for the most part, it abstracts out the hardware details. The hardware details get picked up in domain-specific architectures, and was the purpose that we developed in this case, the SUAS reference architecture for. Initially, it was intended to service that 3-course specialization track that I just talked about, but it's also serving the purpose of facilitating the research as well. It is focused on the functional and physical definition, and it's growing in use within the AFITs, within our flight test activities. We're now getting ready to go into our 3rd year of use with the SUAS reference architecture, whereas on the first one, we're really in our 1st year of application with that. We've been developing it over the past year or two, but this is the first year we're really doing an application within that autonomous systems reference architecture. So a little bit of what we're trying to do with that. Again, accelerate the learning, facilitate the collaboration, providing a continuity across multiple projects. We want to be able to support that rapid prototyping cycles. This has got two purposes. One, we want our students to know how to facilitate those rapid prototyping cycles when they leave here, go on to their jobs in the Air Force, but we also want to utilize that while they're here so that we can get further faster with our research. We'd like it to be scalable in scope, and as I mentioned, we'd like it to be relatively domain agnostic so that we can develop autonomy approaches and then apply it to whether it be ground vehicles, air vehicles, maybe even space vehicles. A little bit more about what it is. It's a SysML model defined in Cameo System Modeler. It's got the structure to support everything through ConOps requirements, function. We say hardware, software components. It tends to abstract those out because, again, we have the domain-specific reference architectures to pick up the details for that. It does have the provision for interfaces, messaging, and all that good stuff as well. The modules, they're intended to be model-driven for compatibility. The idea is develop different autonomy modules and then be able to reuse them, swap them out for new modules or as a particular mission set dictates. So we want to provide these, again, as component libraries, as well as provide some example autonomous agent builds. We want this to be easily transitionable to hardware configurations, and I'll talk a little bit more about how we do that as we get a little further down here. And we want it to be we want to be able to do evaluation of these models, both in a simulation environment, but again, be able to transition to hardware experiments as well. High-level overview, this shows one or more agents interacting with an environment, and it can interact with that environment either through actions, communications, or perceptions. You know, if the agent has some sort of sensor on there or multiple sensors, it can perceive things from the environment. The meat of what the autonomous systems reference architecture is really doing is in that sub-block on the right called agent, okay? And because that is where the autonomous systems software agent resides. And that's really, again, the focus of what this initial, the higher level reference architecture is intended to do. Diving down a little bit, so that's starting to explode that agent. On the left-hand side of that is the hardware. Again, although you could build all that hardware definition within the autonomous system reference architecture, we're spending less time doing that because the other domain-specific architectures have all those libraries and example builds all ready to go in that area. The meat of what the autonomous systems reference architecture is alluded to on the right-hand side under that autonomy column, and in particular the block within there that says software agent. Okay, that is where the different algorithms and the interplay between those algorithms to achieve the autonomous behavior needs to occur. And so we're going to blow that one up here next. So here is a blow up of that software agent. We're utilizing some work done by other faculty. Dr. Bert Peterson was one of the ones doing work in Hammer architecture or hybrid architecture for multiple robots. Shows that there's 4 levels here. Working across from the left there, we've got a controller that manages the behaviors and their implementation. We got a sequencer that enables and disables the behaviors as required and maintains knowledge of the internal state to determine whether or not a new plan is needed. The deliberator does the higher level reasoning task to determine whether or not we need to change modes of operations or is a new set of behaviors going to be required. So task allocation and planning within the individual agent. And then we've got a coordinator that really focuses on when you get into cooperative control, expands on the capabilities of the individual agents, allowing prioritization, managing negotiations amongst other agents. And so all of these are defined modules. We've got defined information going between those modules and even format for the information being passed between these modules. Okay, we'll talk a little bit more about what's in there, but I want to introduce the application that we're working on because it'll make it a little bit clearer how we're implementing things within this framework. Our initial application is a wide area search and surveillance concept. I've got 2 Air Force lieutenants, Katie Cheney and Dave King, are working this problem for us. The concept is you have multiple autonomous and or cooperating agents. They've got to find targets in an uncertain environment and maybe maintain surveillance or actually engage high priority targets. Just because they fly over a target doesn't mean they see it. Even if they see it, doesn't mean that they're going to know exactly what it is or where it is for that matter. So there is imperfect navigation and geolocation. We can have imperfect inter-agent communication in there. And likewise, there's limited mission time. So if they spend too much time doing one task, they may not be able to get to another one. Autonomous objectives are things like search, surveil, engage. And then where we implement cooperative behavior, we can do things like redirect search to fill in a search area that maybe another agent is not able to cover, do cooperative confirmation of a target that's been found to help reduce false alarm rates, expand surveillance, or even help engage a target. And again, all of those decisions come at the expense of, well, if I've got to do these things cooperatively, I'm not searching on my own for new targets. So a little bit of how this is going to play out. Initially, we're going to look at doing this with one ground station, multiple multi-rotor agents, but one of the iterations we'd like to do on this is show that we can very quickly switch between multi-rotors and fixed-wing vehicles without having to redefine the software agent associated with the autonomy of the vehicles. So we'll start it initially with the multi-rotors and then switch gears over to the fixed wings. So again, in terms of the autonomous objectives, ingress, egress to get to the search area, do search and detection, target confirmation, surveillance, and then where we implement cooperative behavior, we'll be doing things like initially we're going to do this with local decisions based on globally broadcast information. It's easy to implement. The other reason we like that, at least to start, is it degrades gracefully. If you lose a particular agent, it's just one less agent putting information into the network, if you will. But you're not dependent on any one particular agent. But we will, down the road, we expect to investigate some centrally determined and or negotiated decisions as well. And with the cooperative behavior, what's going on is the agents are weighing the benefits of continued search or surveillance on their own with the intent of finding additional targets with the potential benefit of doing cooperative confirmation or surveillance. Talking a little bit more about those objectives, they can get broken down into lower level behaviors. And even those behaviors themselves, you can have composite behaviors that are composed of multiple lower level, either composite behaviors or atomic behaviors. The example shown here on the left shows a behavior called avoid and go to waypoint. And as you might guess, that has really two lower level behaviors, go to waypoint and avoid obstacles. Even those behaviors, that may be all you need to go down to in terms of defining behaviors, but even the go to waypoint, if you think about the system functionality required to implement that, that's going to eventually have to be mapped to multiple system functions, things like navigate, fly, locate yourself. Okay, so all of those are lower level functions that would be required just to achieve the behavior of go to waypoint. And obviously, if you're building a vehicle, those are important things to know because you've got to allocate components to do those functions. Going back to that software agent chart. So this talks about where we're going to put some of these decision rules and other algorithms that we're developing for this particular application. The health and status monitoring, and generating the behavior hierarchies, that's going to be done in the sequencer. Okay. The deliberator is going to, that's where your state machine exists, implementing the local decision rules. On the right-hand side, the coordinator is what's going to be interfacing with the other agents and implementing these cooperative decision rules. Under the perceptor there, that's really the sensor and estimation models. It could be as simple as a basic seeker model. For instance, one of the things we're going to do is just project a footprint below the vehicle. If an object appears in that footprint below the vehicle, it will do a probability draw as to whether it sees it and does it identify it correctly. And so that's a very simple model for a perceptor in this case. Simulation environment, we intend for this to be flexible in terms of what types of simulators that you can implement this with. And we want to be able to proceed through rapid test and evaluation cycles. Initially, we're going to be utilizing the Autopilot software in the loop simulator associated with the Pixhawk autopilots. If anybody's ever worked with those, they're the firmware that runs on the Autopilot. There's versions of that can be paired with the dynamic simulations to run software in the loop. And so we'll be able to take advantage of that directly. The wide area search and surveillance is going to handle the world model consisting of targets and non-target objects, and it'll interface with where the vehicle is in order to determine what could be seen by the vehicle given its location. We're looking at a couple of different simulation environments to visualize that. Microsoft AirSim, Gazebo, and AFSIM are the ones that we're looking at right now. And I think AirSim and Gazebo we've already done some preliminary work with, and AFSIM is next up to look at because it's of interest elsewhere in the Air Force. Test plan, and this is something that's really going on right now. I expect a lot of this is going to be done by the end of the calendar year. Design parameters that we're looking at varying for this initial evaluation, area coverage rate, which of course is going to be dependent on either altitude, field of view, speed. Similarly, sensor quality, that will determine its ability to detect and correctly ID targets and avoid false alarms. Target and false target density will be varied in the environment. Task priorities can be varied. And then some of the response variables that we're looking at there is, you know, percent of the targets that get detected or ID'd or surveilled for that matter. False alarm rates, coverage, ID confidence, responsiveness, how quickly it reacts to changes in the environment, robustness, how well does it do if you design it for one set of scenarios and you throw a different set in. On the right there is just kind of an example of a trade space analysis I did, quite a while ago, but it talked for an individual agent trying to implement a autonomous target recognition algorithm. You always have a balance between probability of detection and false alarm rate. And based on where you sit in the balance of those two parameters, it may make a big difference in whether or not it's beneficial for you to cooperate or operate the two agents autonomously. And so the surface plot there, as you go low, it says it's actually hurting you to cooperate. As you go high, you're getting a benefit from the two agents sharing information and making decisions based on each other's information. And so the trade space analysis like this can help you understand how you phase in this cooperation in order to truly improve your overall mission effectiveness. Okay, as I said, one of the goals of this whole effort is to make sure that we can transition this to hardware experimentation. So some of the challenges here are similar to what I talked about before. We spend a lot of time bringing students up to speed, learning the domains, learning what's been done in the past. We'd like to accelerate that learning curve. We oftentimes get inconsistent quality associated with the architecture builds. And oftentimes the analysis was pretty much disconnected from the architectural design itself. And that's not a problem just in the student environment. I've seen that same problem in Air Force programs. So the lower level architecture, the one that reference architecture, the one that's focused on, in this case, the SUAS domain. We want to improve that student learning, teach SEs to the non-SEs, capture that extensive knowledge from all the projects that have gone before, and provide that basis for the follow-on research efforts. Some of the, we've got quite a bit of experience in doing this. This is some pictures of recent flight tests showing the extent of our vehicle builds. On the upper right, that's our lab, and you'll see about, it wasn't even set up to take that picture. It just happened to be one day we came in and noticed that there was vehicles all over the place. And somebody said, well, we ought to take that picture just to highlight the extent of the work that we're doing. And so you see some bigger vehicles hanging from the ceiling. You got all kinds of multi-rotors of various size on the table. If you look in the back, you got some trucks as well as some other multi-rotors as well. Lower right was some cooperative work that Jeremy Gray did when he was a student here. And you'll see about 6 different vehicles in the grass there. All of those were had to be put together in order for him to do the variety of tests that he was looking at for his work. So the small UAS reference architecture, what's in that? Okay, I know this is probably going to be difficult to read for a lot of you, but I'll talk you through it. If you open up the reference architecture, you get to the home page. On the left-hand side is nothing more than a set of version notes. And as I was developing this, I said, well, it'd probably be worthwhile letting the students and the people working with me know where I am with the build of this architecture, what's working, what's not working. In the top center is the component library. And so you've got packages associated with vehicle components, ground station components, mission parameters, payload components, etc. And I'll show you what some of those libraries look like here in a minute. And then on the right, you've got example builds for both a multi-rotor system model and a ground station. And again, that's to show them typical builds. It doesn't mean they have to build it that way, but it shows ways that they've been effectively built in the past. And then the lower middle package has a more complete concept laid out, everything from requirements and use cases to functions and a system build. Okay, and I'll walk you through a couple of these in the next couple of charts. So one of those component libraries shown here for the ground station. Again, the pre-built component blocks to facilitate that rapid design and reuse. You see in here, you got a ground station computer. It can be typed by the type of operating system that goes on there, which obviously is going to be important when you start to identify your software modules, whether it be for image processing in this case or ground station software. Likewise, other things, GPS base station, a Wi-Fi hotspot if you need that, RC transmitter for a safety pilot. Maybe you need an antenna tracker. Okay, all of their pre-built ports that we know about are already predefined on these blocks. Here's another part of the component library. This one is for connectors, and if anybody that's ever worked with integrating COTS, commercial off-the-shelf components, knows that the connectors can drive you crazy. You want to connect one thing to another that should work together, but you find that the connectors are incompatible. So I put some effort into defining all those different connectors, pre-typed ports to facilitate that COTS integration again. Just as examples here, you notice I've got HD video ports defined, and I can type that port by 5 different HDMI connectors. At least those are the 5 different HDMI connectors that I know about. USBs are even worse. We have run into 7 different types of USB connectors in the work that we've done here. And it's important to know when you pick a component, what type of connector is native on that. Do we have to change it out? So the way we use this is starting with the UAF Specialization track, we give the students a draft CONOPS representing a user's capability needs, typically from a DoD sponsor. And then they have to break that down and do a functional decomposition, establish a set of requirements, and vet those with the sponsor. And then go through the conceptualized design, build, and flight test in response to that concept. We involve the sponsor in the design reviews. At a minimum, we'll do a preliminary design review, critical design review, system verification review is the final out brief, but they also have to do a test review board, safety review board before they're allowed to fly as well. Some examples from that. So here was RTS, in this case, stands for Remote Targeting System. And so here's a use case diagram depicting a larger use case model. Those use cases, if you recall back to what I was talking about with the autonomous systems reference architecture, there was behaviors or objectives and composite behaviors defined for those software agents. Well, these use cases can oftentimes be directly correlated with those objectives, autonomy objectives. The pitchfork symbol there indicates that there's lower level decomposition in the form of activity diagrams for each of these use cases. And so here's one that shows for the surveil use case. I know it's hard to read, but this now goes beyond defining these behaviors from the autonomy sense, but starts to, it helps us identify the individual system functions that are going to be necessary in order to realize it. So, for instance, starting from the lower left is a path associated with capturing the video and sending video, in this case, down to a ground station. Moving in one column from that, if I'm going to fly this surveillance pattern, whether it be alert or anything else, I have to be able to perform controlled flight. So that's what that's doing. There's another one with an operator monitoring what's going on. In this case, it was more semi-autonomous. So that provides or defines the required system functions, and again, those can be traceable to the composite behaviors from the higher level reference architecture. Collection of all of those across all the use cases helps us to identify the total system functionality, down to the levels necessary for specifying subsystems and eventually componentry. An example BDD from this one. In this case, this is for the vehicle, not so much the UAV itself, okay, but the vehicle consists of everything you would need to fly minus the autonomy. So it starts with a stock airframe choice in this case, and then the students had design choices to fill out based on what motor, prop, batteries, things like that they wanted to put on here. And that makes up the total vehicle. You combine that with the autopilot communication, payload equipment, and now you've got your announcement. Internal block diagrams. So this one shows, explicitly represents the ground-to-air linkages. In this case, it was 3 different linkages between the ground and the air. One associated with the autopilot telemetry control system, another one associated with a backup safety pilot, and a third one associated with the imagery. But it allows us to explicitly represent those linkages down to the components that facilitate them. Within the vehicle, okay, another IBD. This one now provides the build to schematics down to the individual components. And this is important to be able to not only make the decisions of what needs to go in there, but to document what the build is in case anything needs to be changed. We're trying to do more and more with building constraints and requirements checking directly into the architecture definition itself. So here's an example, a portion of a parametric diagram where it shows some constraints associated with endurance and range calculations and roll angle and turn rate calculations. The roll angle is important because if you're going to do surveillance of a target with a fixed camera on board the vehicle, you need to know for a given airspeed, given turn radius, what's going to be your roll angle, and in order to orient the camera so that it's looking at the center of that loiter when you're in that mode. And obviously, for anybody who's worked with these parametric diagrams, you see them, the inputs and outputs of these constraint blocks being tied to the property values of the various component blocks. So question is so what? Is this helping us? Yes, as I said, we've been through 2 cycles of the UAF specialization track now, and we've seen a big improvement in the quality of the designs and the analysis coming out of the student group. Directly from their architectural definitions, we're seeing some nice things in terms of cost versus performance trade, weight versus endurance, battery capacity versus endurance, hover times, ground resolution versus camera and operating parameters. All of that stuff is being able to calculate directly from the architectural definition. This allows them to tie their trade studies to the architecture itself. You're able to demonstrate that their requirements are directly being traced to component selection and performance parameters for those components. And then likewise, when it gets to testing, what are the test cases? Why are they doing those particular test cases? Real quickly, some research employing this. We did, going back to some of my Intel analysis days, we're looking at using some of this architectural work to look at exploitable aspects of rogue SUAS. We're interested in what we can do with this technology, but we're also very cognizant of the fact that we don't have a monopoly on small UAS technology. So we're very interested in what other people are doing with it, how can it be countered. We've had other students look at tying these architectural definitions to reliability analysis. And then finally, some work I'm doing with Ray Madicky out at NTS is he's got a method for parsing SysML architectures to provide inputs to the COSISMO cost estimating tool. And so Ray and I hope to continue that work here in the future. So, and then final chart here before I turn it over for question is we want to demonstrate the multi-domain application of that autonomous system reference architecture. Initially, we're going to just demonstrate that we can move between multi-rotors and fixed wings, but eventually we'd like to carry that to ground vehicles and then maybe even some work in the space area with the CubeSat guys. We want to put some additional parametric analysis in the small UAS reference architecture, more performance calculations, greater use of requirements verification, things like that, and maybe better integration of MATLAB, just as a more full-featured analysis tool. Another thing, we're Air Force, but in order for us to fly, we have to jump through quite a bit of hoops. And that has design drivers in its own right. And so there's thoughts about how do we tie in issues like airworthiness, flight test safety, cybersecurity into the architectural decisions as well. And then finally, I've got a student taking what I did with the UAS reference architecture and doing something similar for the CubeSat area. So the guys doing rapid prototyping of CubeSat have the same advantage in terms of libraries of components, pre-built and example builds. And then we also want to investigate the tie-ins between the autonomous system reference architecture and the CubeSat architecture as well. So that's my talk. I'll be glad to field questions. Mimi, I'm not sure how you want to do that part of it.
Well, I'll leave your deck up because there was quite a few questions, and a couple of them reference specific slides.
Okay.
But we'll try and get through as many questions as possible in our remaining time. One of the first ones that came through the chat, let's see, reference slide 10. What about the human aspects of the system? And I know this is something that's been brought up in previous talks.
Okay. Yeah, I anticipated that. I probably don't have a great answer. We are working that area. If you look at within the autonomous system reference architecture, the human agent and there's a human augmented agent, and the intent is whether it be whether the human is just interacting without any additional autonomous agents running in front of them, or whether or not they are being helped through software agents. The framework for employing those human augmentation algorithms is in there. We haven't done a whole lot with it within our reference architecture, but there is research going on in that area here at AFIT. Dr. Mike Miller, Dr. Brett Borghetti here are doing work in that area. And we hope to demonstrate tie-ins with the autonomous system reference architecture here in the coming years.
Interesting. We'll have to have some of those folks tie in with some of our current CERC research taking place on that. Mm-hmm. Lisa, you're unmuted, so feel free to ask your question directly if you'd like. Or, let's see, perhaps she's unable to. Her question, which
okay, am I unmuted now?
Oh, you are. Perfect.
Sorry, I'm glad I wasn't unmuted before though. So I had, the first question I asked was, what's the difference between a reference architecture and an architecture for a particular system? I mean, you do go down to a great deal of detail, as you just mentioned, down to the components. So where do we draw that line between it being reference and it being specific?
Okay, the reference architecture is pre-built components and examples, but without specific design decisions being made. So for instance, I've got a block associated with motors and batteries and propellers and even autopilots and things like that, okay? And there's property values associated with those, but nobody's made the design decision that of which particular battery I'm going to use, or which particular motor. Now the example builds may have some numbers plugged in for there, but that's really intended to show how you could construct a vehicle using these blocks, more so than to constrain somebody's decision. The intent is if somebody wanted to use this reference architecture, they would take it and then maybe start a new project folder that reuses some of the existing blocks, but now makes specific choices associated with those.
Oh, Lisa, you're muted again, and I saw that you had other questions, so feel free to continue with your questioning.
Yeah, Dennis Beatty used to talk about a generic physical architecture and an instantiated physical architecture. And his the generic physical architecture was, you knew the type of things you needed, you hadn't really made the choices of which specific models of those things you were going to choose. The instantiated architecture or physical architecture was you had made the design decisions. And so so the intent of the reference architecture is to stop at the generic architecture level and leave the specific design decision for the project that is being used on.
Okay, which suggests that you've already done quite a bit of systems analysis so that you have some of those definitions or scope or whatever you want to call them to know that of these multiple different reference architectures, which one would apply. Because in your examples, you showed that multiple people have already published reference architectures on autonomous vehicles or autonomous vehicles related activities. So I guess I'm looking for, you know, if somebody's going to invest the effort to develop a reference architecture, right, how can they decide when they need one and when it wouldn't be valuable? And that may not be an appropriate question for me to ask in this setting. Maybe I can call you. So.
Well, I'd be glad to talk about it, beyond this today. But, you know, really the big thing is if there's a lot of reuse of types of components and patterns for builds. The idea of a reference architecture is, well, let's capture those types of components using pre-built blocks. Let's capture those reusable patterns in terms of how we combine those components, not necessarily to constrain that it must be built that way, but to indicate options. Okay, and maybe help some new folks understand that that maybe there's some components you haven't thought about that you probably ought to include. For instance, overload protection on circuit. You know, a new student may say, well, let's just keep on loading things on that power line, and somebody, you know, an older, wiser person may say, have you checked your current loads on that circuit? Oh yeah, well maybe I ought to do that. So things like that.
Thank you. I'll let someone else ask questions now.
Thanks so much for the questions. I know we only have a minute left, so those unable to stick around, Dave, I'm not sure what your time constraint is. If you wouldn't mind continuing to answer questions after.
I'm okay. I don't think I have anything backed up against me.
Okay, perfect. Continue next. William Bishop had a question that said, can you explain the relationships between reference architecture and reference models, as well as any experience applying reference architecture to software product line engineering?
Okay, I can probably do a better job of the first one, maybe the second one. Okay, reference architecture versus reference model. The reason I called out a reference model is because Kaslow and Ayers, that's what they referred to theirs as. Okay, they referred to it as a reference model, not a reference architecture. And so I was respecting their choice of words. Now, if you look at what they did in their reference model, it certainly encompasses some of the same things that the OSD reference I talked about says should be in a reference architecture. So in my mind anyway, I don't think it would be incorrect to call this a reference architecture. Now, we are building upon what Kaslow and Ayers did, and we're adding to it. And what we're adding to it that's not in there right now is this notion of the component library in the example builds. And we're doing that because the prototyping guys at AFIT here doing CubeSat says, hey, that would be really useful for our students doing CubeSat work. But again, the reference model was really just their choice of words, not mine. With regards to the second half of that question, Mimi, could you repeat that?
Sure. It's did you have any experience applying reference architecture to software product line engineering, which I know kind of goes outside of it?
Boy, that's not my strong suit. And you know, product line or software product lines. Boy, that's probably one I probably don't even know enough to stay out of trouble, let alone get myself out of trouble once I get into it.
Fair enough.
I'm not a software guy. I'm aeromechanical and systems, not so much software.
Fair enough. We have another question from the Navigator group. Based on your learnings, are there any standard tech data deliverables you would ask for a UAS?
Well, what we're doing with, in keeping with the rapid prototyping cycle in terms of deliverables, we are asking for the architectures, the architectural models themselves, but we also ask the students to organize the views to walk somebody through the thing. And so we don't want them to produce a whole lot of documentation outside of the models, because we think really the authoritative definition is the model itself. And one of the things we think is very useful with these model-based SE tools right now is the ability for them to generate HTML reports that you can then provide to anybody, regardless of whether or not they have the MBSE tool that it was generated from. And now then that allows any individual to parse through the model and see the particular views that may be most important to them. So we're trying to really emphasize the use of the model directly rather than produce a lot of documentation from the model, because as any number of people will probably tell you, as soon as you produce a report from the model, it becomes obsolete as soon as somebody goes back in and changes something in the model.
I think a lot of folks have experienced that issue as well. It looks like there's a couple questions that are referring to access to your library, or if there is a common repository environment that others can learn and iterate on from your library. Like if you have any documentation of your methods that other labs can adopt.
We haven't hosted our model on a public site. But I will say there's nothing about our model that is sensitive or proprietary. We're government, so it will not be copyrighted or trademarked. That's good news for everybody that might want it. I would have to put the full model through a public release, but I don't anticipate that would be a problem.
Excellent.
It is our intention to share the model. Matter of fact, one of the things I would love to see is other people maybe taking a look at it, telling me what they think, telling me what they do differently, so that we can improve it.
Fantastic. I think a couple of folks would be interested, and we could probably connect you at the year-end event at SERC Sponsored Research Review to follow up on that part. Let's see. That answered a couple of folks' questions. They were asking if it was available for external use.
Yeah, the small UAS reference architecture is a little bit further along in terms of maturity, and that one again, I'd have to go through the clearance process, but I don't have any problems with sharing that really as it is. The autonomous system reference architecture, we're trying it out with the wide area search application for the first time, and I don't know that that's ready for prime time until after we get through this first cycle.
Perfect. And then Andrea, you're unmuted, or you're available to unmute yourself if you wanted to ask your question directly.
Okay. Yeah, my My question was about kind of modeling the behavior, and if you ran into trouble, trying to model some of these behaviors up with just activity diagrams and what issues you might have had there.
No, actually. Now I will tell you some lessons learned that I found. And this is if you want to reuse these activities, okay? What I found is go through, for instance, on the small UAS reference architecture, if you're starting from use cases, you break those down into steps of a flow and identify your activities, okay? You're better off creating those outside of the activity diagrams first, and create your library of activity from, say, a comprehensive set of use cases and all their flows. And then when you build your activity diagrams, you use instances of those activities, not the activities themselves, but an instance of their activity. In Cameo, it comes across as a call behavior action. And so it's stereotyped by a parent activity, but you can now, you can have multiple instances of the same activity in the same use case or in the same activity diagram, or you can have multiple instances of the activity across different use cases. And so I learned that the hard way. But in terms of being able to model down to the level of detail I needed, no, I found it was somewhat straightforward to break down the use cases down to the lower level actions sufficient to identify the componentry that's going to be required to perform the actions. And that was really our goal.
Yeah, and I guess, so you didn't find a need to have to worry about maybe not being able to determine exactly the action that the system might take. You just specified kind of to the level of detail you knew the component needed to do.
Well, if it's an available component, okay, again, a lot of what we're doing for the small UAS as well as the CubeSat area is we're integrating COTS componentry.
Yeah.
And so we know what the COTS components do. And if we get it down to, a simple example is, oh, I need something to transmit video. Oh, okay, well, I can buy off-the-shelf video transmitters. Okay, well, the action is transmit video. I need an input from a camera. An output is some wireless signal coming out of a video transmitter. Assumedly, I need a video receiver on the other end as well. But
yeah,
now,
okay,
where it's a little bit more complex is something like an autopilot has multiple system functions it can perform. Okay?
Yeah, and I think as these systems become more and more autonomous, I wonder how easy it is going to be to specify their behavior and figure out all the functions you need. That's kind of what I was wondering about.
Yeah, what we're finding with the autonomy is a lot of the lower level functions are there, but it's a matter of how do I group these, and this is where the behaviors from the autonomous system reference architecture comes in. For instance, if I'm in search, okay, a behavior might be search. Okay, but in order to search, I've got to be able to perform controlled flight. I've got to be able to navigate. I've got to be able to operate a sensor of some sort. And I've got to be able to make some decisions based on the data that sensor is collecting. So there's a whole lot of system functionality that may fall out of one of these autonomous behaviors, and that has to be broken down. And that's kind of where we where we're drawing the bridge between what I'm calling the autonomous systems reference architecture that identifies these composite behaviors. And then on the other hand, the domain-specific reference architecture, maybe the UAS one, that says, oh, okay, here's all the system functionality that you're going to need for those behaviors to be realizable.
Yeah, thanks. That's interesting.
Oh, sorry, I was still muted. Let's see. Looks like another question. Pascal, you're able to unmute yourself if you'd like to ask directly, but just jumping into the question right now. It's on top of the architecture description, which is a design solution, what about to create an executable specification model of this architecture to enable its early validation by simulation? Then why not modeling an executable architecture design to enable automatic verification? And I think you kind of mentioned that as well, versus the validated spec model.
Okay, well, there's a couple of areas where we're doing validation verification. Okay, if with some of the constraint relationships, and I showed examples of those on one of the screens there. The segment of a parametric where was that? Yeah, so this was a portion of a parametric diagram. And so that is showing some aspects of, call it requirements verification. So if I had a requirement that said on endurance or range, based on the parameter choices for the various components and the combined weight of the various components and all that stuff, it can do a calculation of, well, do I project that I'm going to have enough endurance? So we can do some requirements verification right now. Likewise, we can take those activity diagrams and test the flow logic associated with the system design. Okay, Cameo in particular, it's not the only one that does this, but Cameo allows you to create executable models of your activity diagrams or state machine diagrams for that matter. So that's another way you can verify operation of your system. And then the third aspect of that is through more full-featured simulation. And that's where we're taking advantage of the software in the loop environment to, okay, now let's put this with an actual vehicle model with the autopilot driving a vehicle model, and we can have our autonomous software agent interacting with that software or with the autopilot software to test out whether or not this works. We were able to do this over the past year with some swarm behavior tests. We had 3 multi-rotors that were flying in close proximity, and we were doing a variation of Reynolds rules for flocking. And we tested it all out in software in the loop before we went to hardware. And that made the hardware experimentation a lot easier to get to. Now, I'm not going to say it went flawlessly when we went to hardware, because some things like bandwidth and time delays aren't always represented well in software in the loop, and sometimes those things can bite you in hardware. But as far as the logic and the autonomy software agent, that was all developed and tested out in software in the loop before we ever moved to hardware.
Thanks, Dave. Kind of going back into sort of the basics and more semantics, another question was, what is the difference between a behavior, a use case, or a scenario?
Okay. Well, this is something we continue to argue about here. And the reason being is, and let me give you a little background. The stuff on the autonomous systems reference architecture, a lot of that is coming from the AI community. That hybrid architecture for multiple robots, unified behavior framework, that's coming from the AI community. And then along, I come from the SE community, and I say, well, okay, I want to.
Oh, Dave, are you still there? It sounds like we lost you, or at least lost your audio. There we go. Got you.
Okay. So we tend to refer to behaviors from the autonomous, the autonomy side of things, and behaviors tend to be composite functions, composite set of functions. They might be easily mappable, and oftentimes they are easily mappable to use cases from the SE side of things. For instance, I can write a use case for search. And within the use case, I can define the fact that I have to be able to fly, I have to be able to run a seeker, I have to be able to run a detection algorithm, and all of those things have to come together. I can write a use case to do that. On the autonomy side, they may be more, okay, I want this thing to do search. And they don't, sometimes the autonomy folks don't get into the nuts and bolts of how do I actually realize the hardware and the software to actually perform that search now. So we continue to struggle a little bit with bringing these two communities together, the AI and the systems engineering community. We hope to have later this year kind of our best hack at a glossary and an ontology of how this all relates. You know, when we talk about behavior on the autonomy side, how does that relate to system functionality on the system side? I expect I'll have something later this calendar year that I can share with people.
Excellent, much appreciated. Another question that refers to specific slides 14 through 16. Is it strictly autonomous versus automated?
We're doing both, okay? From a purely, where this becomes a philosophical argument to some, okay, in terms of automated versus autonomy. From an individual autonomous agent, you could argue that we're not doing machine learning. You could argue that is automated. But when you start to combine this with other agents, we are getting into higher level decision making. For instance, an individual agent deciding, is it more beneficial for me to search on my own or contribute to a cooperative confirmation or surveillance task. So we are doing more and more complex behaviors on these. But I have had some people argue with us saying, oh, but that's just automated. You know, when we do swarm behavior, for instance, we tell it to, you know, search via this pattern with a multiple group of vehicles. So they all have the same search pattern, but they all have to avoid running into each other as well. You could say that's a directed task, but there's a lot of local decisions that have to be done there because, oh, well, I want to progress towards this waypoint, but I also got to avoid these other vehicles that I'm flying with. And so it's constantly having to evaluate its real-time actions in order to do that. I don't know if I answered the question on that one. But...
I think so, and it probably brings up a lot more questions as well. Another question that refers to a slide, and I'll jump to it. It was slide 26. Or it was more of a comment that should be expressed that the value of involving the stakeholders and sponsors is important and helpful at design reviews. I agree, as this is something we do extensively with our models.
Okay, well, yes, our sponsors are, we've been doing the small UAS development track for about 7 or 8 years now. The past 3 or 4, we have gone to sponsored projects for them. And so the sponsors come in with that, or we develop that draft ConOps with the sponsor, and then we try to schedule sessions with the sponsor where the students come up with a set of requirements that they think are reasonable, and they have to present that and get feedback from the sponsor. If they ask for relief on certain aspects of the ConOps and or set of requirements, they have to approach the sponsor and say, well, how important is it that it be able to do this? Suppose it can only do this. So we, to the maximum extent possible, we involve the sponsor throughout, but at a bare minimum, the preliminary, critical, and design reviews and the final outbrief. But absolutely, we think the part of what we want to expose the students to is that you're not doing this for yourself, you're doing this because somebody has a need out there. And it's important that you try and satisfy their needs.
Definitely. I think that's something we mentioned in a previous talk related to DevOps. But actually, this all kind of relates to another question that was asked, which was how the requirements were managed in baseline. So you're saying that it was sort of incrementally done at different points with the students and the sponsor? Or is there?
It is part of their model. Okay, within Cameo, they have a folder of requirements. Those requirements are traced to functions. Those functions are allocated to component. All of that stuff is tied together. And that's part of what the students are graded on is your model comprehensive and complete? And if they change their design, without changing, their design or their build without changing their model, that's bad. Okay, because at the end of it, when they get to that system verification review, we want to see a model that relates to what was flown and how it performed. And so, yes, requirements are an inherent part of the model-based SE approach. And likewise, when they go to test, okay, tell me what requirements you're testing to with this particular test point.
Excellent. So it's kind of incorporated already. I feel like this was kind of already touched upon. And unfortunately, Dave had to leave, but he was saying that he was having trouble reconciling the top-down approach to autonomy and the ASRS and the bottom-up applique approach in the SUAS, making the system a little more autonomous can change the block diagram at all levels, right? Oh,
absolutely. Autonomy is an allocation decision. And for instance, some of what I showed for the remote targeting system, I mentioned that was really a semi-autonomous application for that particular one. And if you recall in the activity diagram, I showed a video being sent down to a ground station operator that was monitoring it. If you could replace that whole path with a target recognition algorithm running board on the vehicle, so that conceivably you wouldn't even need to bring down video. If you were confident enough in the vehicle's performance, you could trust in the algorithm and say, nope, let it go. So absolutely, the decisions on autonomy and what you're able to achieve with autonomy will definitely affect your system, your lower level system architecture. What processing you need where, what communication links you need, because the more you involve the human in the loop, probably the broader the links that you need to bring down to get that information to the user.
Got it. And as we're coming up to 2:30, I really appreciate you sticking around to answer the questions that were posed, and I'm sure it sounds like a lot of this is leading into further conversation with you. So hopefully. Well,
let me give you a commercial. Okay, yes, I certainly hope to be there at the SERC annual review in November. I also, myself and Jeremy Gray, will be presenting this work. There's two separate presentations, one of them on the autonomous systems reference architecture that Jeremy will give, and then I'm going to do one on the small UAS reference architecture in a rapid prototyping environment. Those are going to be presented at the NDIA System and Mission Engineering Conference later this month. I think my talk is, both those talks are on Wednesday morning of the NDIA event.
Perfect. I know a lot of our government participants that are on right now will be attending that as well. For everyone else, there's the annual event on November 18th and 19th at FHI 360 in Washington, D.C. We hope you'll be able to make it. And again, Dave, thank you so much for your time, and thank you everyone for joining us.
Sure. Thank you all.
Thanks. Take care, everyone.
Okay.